Yeah, so today I'm going to talk about, I'm the director of the group, so in some ways I get this odd feeling I sometimes get to talk about other people's research. Uh, and it tends, but this one is a project that I really like because I think there's some glaring omissions in where the industry should be. So this talk will talk a little bit about it. But like Michael said, this is a slide to sort of show you what Autodesk does. There's a lot of stuff in this slide. Autodesk came from the world of AutoCAD. That was success through 2D drafting tools, right? And then the world sort of became, or the software became capable of supporting 3D. So we do the range of stuff from designing cool shaped cars to software to design power plants, consumer products, buildings. In the upper corner, I actually got into this sort of through a funny way that I was doing user interface design and interaction techniques and got involved with this little company called Alias that wanted to use my interaction technique to help animators do animation, and ended up sort of on the media and entertainment side of it. And that's what the octopus face guy represents. I actually was part of the Maya, or led the Maya 1.0 development team. So if you want to blame me for features early on, I'm the guy to talk to. It's a little bit late for changes though at this point. We're sort of beyond beta. Anyway, so being from Autodesk, I'd say we help people imagine, design, and create. That's sort of the company thing that you say. But I run the research group, and I think it's a very cool group because we span a bunch of different areas. And actually, I think a year or two ago, my friend Toby Grossman was here, and he talked a lot about the user interface research group and the stuff that's been going on there. So I decided I would not talk about that again, and I would talk about some other projects that are going on. And you can see there's a range of stuff. On the upper left-hand corner is this sort of weird thing. We're looking at bio, life sciences work. Obviously, think lots of work on design and fabrication. How do you fabricate things? Some stuff about sort of the Internet of Things, which is the environment, and also ergonomics research. The neat thing I always say about that is that we have these really sophisticated tools that design things for humans to use or to be part of or to live in, but we have no fidelity model of a human in these systems at all. Like I can design a version of this chair digitally, do a highly detailed model, but I can't get one piece of information about whether it's comfortable or not. So that's really about the basis of some of our ergonomics research. It's more about, can we describe parametrically the characteristics of a human being. So that's a really cool project. We're also known for simulation graphics research because we come from that sort of graphics background. One of the guys in my group has a couple of Academy Awards for various different special effects, fluids, and stuff like that. And one of the secret sauces of our research group is we actually have an explicit research transfer team. That's a set of really crack developers who can take ideas that come out of research and sort of push them further along and either produce something that's product ready or something that's like some component that a product team can really use and serve as sort of the guys who are the on-call 24/7 to make sure that people using this stuff are happy. The stuff that I'm going to talk about, I think, is one of them. We're sort of at this point of articulation in time where computer-aided design might be changing, and I think it's an important topic. And it's this sort of overlap between computational fabrication and changing the way people really do design and really redefining that relative to CAD in a different way. And so why is this? Well, my take on this is like, well, we're sort of in this digitization. We're in the process of digitizing the making of things. Years ago, when I had more hair and stuff, I used to play in rock and roll bands, and then all of a sudden, at some point, people started digitizing audio, and for me, it opened up this whole world of like, oh, I should get interested in computers because I think I would be able to do a recording studio, much cheaper than having to pay time in a recording studio. Maybe I could do it with digital audio, and it was a very new thing. Turned out that was right, and the digitization of audio really sort of changed things, right? I also found out that analog is super great too. But the way I pitch this talk is, this is what's happening in the world of physical things, right? And there's a good reason to do it. And if you look at the computer industry, and I gotta admit, I'm not like sort of patriotic or person but But I'm actually really proud of the computer industry because like when I started, like nobody was walking around with smartphones and stuff, and people would say, "Oh, you do that computer thing. You use that IBM computer at the university," and now my mom uses an iPad and stuff like that. So we've done really well. Like that's good impact, and I think the reason that they have is because we were really clever about building systems to construct systems. So this is a typical slide where it shows like, look, early computers were these sort of hand-assembled things. Like they're very obviously, components stuck together. And we developed these very high-level design tools and fabrication tools to miniaturize this stuff, to make the whole process of making them a lot more better and a lot more efficient. And it's really paid off. We got some sweet deals along the way, like Moore's Law, but that sort of approach to it, this very systematic approach, has paid off really well. Unfortunately, in the broader world of physical things, this isn't as true, but I'd like to help it along. And so the thesis of the talk is, well, what you really want to do, the good stuff is, if you program the physical world in the same way we program the virtual world, because that's actually very nice. The physical world is all messy and dirty and tough, and that is a lot of fun, but there's a lot of great aspects for digital control of things, and you as computer science people understand that. And that's what we're seeing going on with 3D printing, right? Some of the fun and the goodness and the power of 3D printing is because it has those aspects. And like the computer world, it's really changing like who is capable of manufacturing things or fabricating things, where they can do it. You don't have to go like literally, we go to this little office, it used to be somebody's office, and we 3D print something as opposed to going to a special room because we're going to mix plastics and stuff like that. So literally in that small example, the where has really changed. Also, what you're capable of fabricating has changed. I could never before in my life build a plastic enclosure, but now I've built several of them, and I had some of my own personal projects. I readily, I'm quite well skilled in that. So that has really dramatically changed. And finally, the real gist of the talk I'm going to really focus on is like how the act of designing and fabricating is going to change. And this is the classic example that I show. Like when we brought a summer intern in, and we said, okay, your first project is like make a little stand for your pencils. And of course, in the old days, you'd maybe go to Home Depot, I guess, and get some piece of wood and a drill and drill some holes, right? But now she just did it on her computer and then printed it out, and then augmented it with some electronics so she'd know what pen was in it and stuff like that. So really, that's a really great example of all those things that are changing in that formula. So the obvious key agents have changed, right? 3D printing is enabling people who couldn't fabricate before to fabricate things. I'm going to talk a little bit about what is buildable is really changing in some pretty exciting ways. And finally, what I'm trying to do right now is change how we design things. So this brings up this sort of computer science notion of programmable matter. And the rise of 3D printing is done really well. I mean, you can create objects that you really couldn't create before. Arguably, we're still at the point where it's like, okay, most of this stuff is sort of baubles and trinkets and stuff like that. We're not really, it isn't a magical fabrication machine, but we can all sort of see the promise of it. Whether we can get there is another matter. But it's definitely changed things, and it's enabled a lot of things and made us think differently about the way we approach fabrication and creating things in general. Typically, people say, oh, it's the future of manufacturing. That's really not clear, actually, to tell you the truth. We spend a lot of time thinking about this. Manufacturing in volume is very different than printing one bobblehead in plastic and stuff like that. Possible, much more challenging, yet to be sort of solved. And when you talk to manufacturers about 3D printing, they're not so much looking to replace existing manufacturing processes, but maybe be able to manufacture something that they could not manufacture before using 3D printing. Yeah, Mike.
The classic innovator's dilemma argument would be that while it's clearly inferior right now, over time, like the equivalent of Moore's law will make 3D printing far better at what it's trying to do, and eventually overtake this. Are you claiming that 3D printing is actually just aiming at something completely different and thus will never overtake it?
No, yeah, I mean, I think we're going to get a Moore's law effect eventually. It's just that it's not you saw the stock prices of 3D companies really shoot up, I think sort of based on that sentiment. And we're initially sort of past that honeymoon period. But I think eventually we are going to get there. We are going to get that sort of economy of scale. And I see that happen even with our simple MakerBots at work. We like sort of use them because they're there, because we have 6 of them, for all these reasons. We just, even though it's inferior to a molding or something, and that eventually will just be, that'll push a lot of the manufacturing processes to change. And you've probably seen videos of people who've done, fusion deposition. Basically, we have these railway tracks of 3D printers and stuff. So there's ideas on how to get all that stuff to scale up. So there's no strong physical reasons why that can't be the case. There's just a lot of practical stuff and momentum of manufacturing industries to keep on going. The classic example we have is like we're 3D printing a bicycle, a racing bike. And I always tell the team, well, you picked a bad example because they're so refined. It's a hard time for us to design a racing bicycle that is lighter than the existing racing bicycles because they've hundreds of years of making these things. So manufacturing is like that. Manufacturing processes are very refined, right, to crank out volume, and stuff like that. But eventually, I think they'll have a pretty significant impact. We see it like on classic example is in people making jet fuel nozzles for airplanes. They do it because they can do it faster than the traditional process, and they can make jet fuel nozzles that are more efficient than the ones that they already have on the planes and understand them more carefully. So we're already seeing these sort of high-end adoption of 3D printing.
Well, the typical argument is that it starts out worse, but people don't need anything that's as good as the manufacturing process, say, actually can produce now. So it's like, okay, yeah, you've got this really high-resolution thing, but like to print a spoon, it doesn't need to be that great. That kind of thing. Like, that may or may not actually be the case with most manufacturing down the road. I don't know.
Yeah, it's funny because, I sometimes think that consumers need the more sophisticated thing. Because if you're a manufacturer, you have specialists who can work with metal and stuff like that. But to 3D print metal is very complicated. Even a specialist did it. So, you need to really have a consumerized version of that because it's like dangerous. There's chemicals involved, sort of thing. So there's just a lot more work has to be done to get those things at sort of the consumer level. It's not that they're going to come from the bottom up, sort of thing, or at least not as easily. Yeah, so that's in the industrial manufacturing. But there's great promise within 3D printing itself that you can get just different behaviors out of materials just based on shape. Here's just some simple examples, like a lot of work that's done with mesh materials to get a particular flexibility by printing out lattices. And these are things that you could not manufacture sort of in any other way, right? So that's really the key. And we're starting to see that too. That's the classic example that you use for metal 3D printing. That's a titanium hip cup with a lattice pattern, a microscopic lattice pattern that bone really likes to grow into and has enough space so that veins and blood supply can exist. And people get those implanted every day. So the 3D stuff's getting used. And there's lots of design things that if you're a mechanical engineer or a machinist, like if you look at that lattice work inside of there, you'd probably say, there's no way I can machine that. You'd also say, how the hell do I test that? I have no idea how that particular thing behaves. It's not part of the engineering, handbooks. But that stuff will eventually come. So I think the real juice here is when we combine that sort of thinking with sort of new materials we can work with. And this is just a typical example. You look at the space of materials. There's a bunch of new things we can do, not only with the microscopic shape of things to get different behaviors, but also with the materials themselves. We can have different behaviors within the materials. Classic examples, we're working with Lawrence Livermore, developing a crash helmet, which has different materials for high-speed crash versus low-speed crash. So like tiny little hairs, some of them collapse based on high speed, stronger ones for lower speed, with different densities. And so in the world of manufacturing, you sort of deal with materials, like if you're working with aluminum as one consistent thing. But in the world of 3D printing, you can print varying amounts at microscopic levels. So you can have these very sophisticated designs where material, let's say, varies across the object that you're building. And we don't really have any tools that do that readily. There's not a lot of science. So all this stuff is being developed, but it will be enablers to do a lot of super cool stuff. Plus, there's a lot of different things that we can print, right? We can print carbon fiber, right? That's actually pretty straightforward. We can print fiberglass. We have a fiberglass printer up in Toronto and stuff like that. And you get really, really strong 3D printed parts. It's completely surprising. And of course, there's the issue of scale. Like people talk about, and people have already sort of printed 3D houses or huts and stuff like that. So there's the whole sort of mindset of basically automating a fabrication process is considered to be 3D printing. Yeah.
Progress in terms of the materials being sustainable, like stuff, not imagining 3D printing as a way to just create a bunch of extra stuff that we throw away, but actually being able to somehow reuse the materials again.
Yeah, there's some nice work. Like you can recycle some of the plastics. I think you can, like with the PLA plastics, you can reuse them like 3 or 4 times over and over again. And actually, we're working with a little bit with a startup company in Toronto who has this plastic grinder that you use with your MakerBot. And they're actually really successful in schools because it teaches kids sort of the recycling sustainable thing. But overall, like I wouldn't say like, oh yeah, the industry is focused on that. No, they're just like, let's just get this stuff working, then we'll figure out what we do with it. So, and I don't think there's not any sort of magic. There's nothing like, yeah, I see your point. Like we may be able to get into some materials that are biodegradable because of that. And we are sort of experimenting with that. Like we did this one project where we made building bricks out of growing mushrooms within forms. And so you can make a building out of this stuff. It's very pliable and you can work with it, lay it up like bricks. And we did this installation at the MoMA in New York City. And it was a fairly big structure, like 25 feet high or something and 20 feet wide. And then at the end of it, he just took all the bricks and like just threw them in somebody's garden and ground them up. And they're gone because they're essentially mushrooms and straw. The mushrooms eat straw till they become fat like bricks, and then we radiate them, kill them, and after a while they end up in a garden rather than a landfill. So there's people looking at that. So yeah, so it's kind of interesting if you sort of look at what's the range of things that are programmable. And maybe I'm the only guy in the world that likes this graph, but if you look at things things are either small or large in my world. And normally we build things out of components like bricks, lumber, and steel, and stuff like that. And we assemble those things into buildings and vehicles, right? That's the traditional sort of, in my world, sort of the AutoCAD world of making stuff. And those actually get assembled into cities and factories. And this, when you start to look at this, like the Internet of Things and self-driving cars, that they sort of layer on and apply to this sort of way of looking at the world. And down at the bottom, of course, you have the microscopic versions of those, the material science and alloys and stuff like that we were talking about. This arguably is the non-organic world. As we sometimes say, that's all the dead stuff, although it kind of pisses off everybody that's working on that side of the graph when you talk about their materials being dead. But it is the non-organic, and there is a whole organic side to this. And you can look at it in the same way. At the very bottom, there's like molecular design, DNA, viruses, bacteria, and those assemble into cells and tissues, and those into organs and limbs and organisms, and then to ecologies themselves. Whoops, jump before the last one. Anyway, so I think of all those things as candidates for design. And that's why I like this graph. So you can think, oh, well, can we make design tools? And can we apply some of the things from one side to the other, et cetera, in the world of designing and creating things? And the answer to that is yes. Whoops, let's see if my slides need to catch up here. There we go. There's this great book, Biology as Technology, and it really points out that biology is becoming a more predictable science, right? We can specify certain processes and given results, right? A whole bunch of stuff we don't understand too, but there are some things that we can sort of treat as engineering tasks and literally as building materials. And you sort of see this in the popular press, right? Like we did a project with this company called Organovo, and they looked at sort of what I refer to now as the classic thing. Oh, 3D printing of living tissues and stuff like that. But literally, it's sort of a manufacturing process or fabrication process being applied to life sciences. There's a little bit more subtler examples, and my group really latched onto this one, which we thought was interesting on a number of accounts. This is this wonderful world out of the wonderful work from the Wyss Institute from Sean Douglas and George Church. And what they did is, you can design small physical things using DNA. You can program DNA, a DNA sequence in a certain way, such that if you sequence the DNA and allow it to self-assemble, you can get structures of certain shapes, like they can do a right angle turn or a little spiral and stuff like that. So basic geometric shapes. So what they did is this research project was to create these little things called nanobots. And nanobots are these small little clam-sized structures that float around in your bloodstream. And when they come in contact with a cell that has a particular geometry on the outside of it, the clamshell opens up. And that's what you see here on the right-hand side. And on the inside of the clamshell are the enzymes that cause a cell to shut itself off. And so the little red things are these keys that only open when it comes into contact with the cancer cell. And so we thought, hey, this is kind of cool. These guys are building these tiny little machines, these mechanical machines, using this weird building material, DNA, and they're actually getting results that kill cancer cells. And the funny thing about it was that we were like, hey, you guys are super geniuses. Why are you talking to us? And he says, well, we're using Maya to do this. And it's like really complicated to use. And I'm like, wait a minute, you guys are like manipulating DNA to try and cure cancer, and you're having trouble using Maya? Either you're like, we're really bad user interface designers, or there's something going on here. But it just showed to me, the power of the tool, right? These guys are saying, yeah, we want to do more. It takes us a long time. We need a better tool. And so, yeah, they literally showed us. They had a plugin that they had built for Maya, this sort of CAD version to manipulate DNA, as a geometry. And then at the end of the day, they would like print out the DNA sequence and send it off to China to be sequenced, get it back, heat it in a test tube, shake it, and look under a microscope, and they would see these micro structures, throw them in a petri dish with some cancer cells, and it would kill cancer cells. Turns out that I think the liver also kills these little guys too. So they're working on that now. But anyway, my whole point here isn't that it's a great medical example, which it may very well be, but that this is a fabrication paradigm that within Autodesk we're all familiar with. Oh, you're designing, you're printing, and stuff like that, but using very different materials. Now, if you look at the world of biology, what's going on, and this is from Biomod 2013, and the funny thing is these things that were at one time these sort of high-end things are now becoming these sort of, almost like the robotic building competitions, where if you see the byline there, it says Biomod is a design competition in which undergrad teams compete to master control of biomolecules at a nanometer scale. So they're fooling around with this stuff like it's building blocks, right? And it's not, like just a few high-end PhD students at Stanford, MIT, and stuff like that. There's these events where they get high school students and stuff, and people do legitimate projects of, oh, I've built this bacteria that when you shine a light on it, starts turning left and turns left until you stop shining a light. And so they're engineering with this stuff readily, and they need tools. And so with this stuff all reminded me of the early days of the computer world, where you had people fooling around with computers sort of in their dorm room or at home, these homebrew computer clubs. And here's an image from 2015. This is somebody's dorm room, and they have like an autoclave and some stuff. So there's this, this sort of parallel going on. This stuff is starting to rise up and starting to feel like that paradigm that we're used to, from the computer world and also from the design mechanical world. So hopefully it'll give you an idea that sort of the range of things that we think we can design with is changing. So I'll stop talking about that, and now I'll talk about how we design is changing. And I think this is the one that is probably, one of the most important ones at this particular point in time. So we joke in our group, actually in Autodesk in general, that although we built this industry computer-aided design, the computer is not doing a lot of aiding in the design. Really what you're doing, the computer is forming as a means that once you sort of figured out what the design is, you type it in to document, and then you use it as a communication tool to show it to someone else. And I was saying to the folks at lunch, sometimes you use it as a litigation tool to describe to someone that they didn't build the right thing for you. But the point is that there's not a lot of smarts coming from the computer to actually aid you in the design. I'm always surprised. It's like the computer is sort of the last person in the room to know that I'm building this out of wood with 2x4s. And it's like, really? I mean, I thought that was kind of, the computer was good at stuff like that. But if you look at the way we design things, it's actually even screwier. Because suppose you're going to design this turboprop blade, right? Now, you actually have some, and you have some requirements for the design, right? You want a certain amount of airflow, and you will tolerate only a certain amount of noise coming off it. These are, of course, completely simplified, but it's just for the example here. So state of the art is this, right? You take a software like Autodesk Inventor, right? High-end, 3D modeling for mechanical engineering, and you build a nice geometric model of the shape, and then you run simulations on it to verify that indeed you're getting something that's close to the requirements that you want, right? And so what they say in the design world when you talk to manufacturers is, yeah, that's the way it works, and you keep on doing that till you run out of time or money. Because you're on a project, and you're getting paid for it, and you have a certain fixed amount of time. So if you're lucky enough, you can maybe do 2 designs, or maybe even 3, and then pick the best out of the 2. But that does not happen all that often, actually, in the design world. So people generally are just going straight towards what is a good enough design that meets the requirements. But it's really strange, because what you're doing here, ultimately, is you're trying to maximize or minimize some of the attributes of the problem. And there's additional constraints. You want to build this thing so it fits on a 1/4-inch shaft, so it fits within a 4-inch space. That's the real requirements for the design, not the shape, right? I think that's the thing that freaks most people out. It's like, well, no, but when do I program the shape? No, but that comes from the requirements. And so this insight is not new to us whatsoever. I mean, the notion of goal-directed design has been around for a long, long time. And this is the notion where rather than inputting the shape of the thing that you want to solve the problem, you input the actual goals of the design and the constraints of the problem that you're working on, right? Then, in order for this to work, hopefully the computer can automatically generate potential designs, and the computer evaluates the designs to see if it meets the needs. So that's pretty standard stuff. So how would this work? Well, as you saw in the previous example, you get the computer to generate 3 designs, and then it would pick the one that's most appropriate, right? And the nice thing is how this thing sort of scales. Like, if you have more computer power, maybe you do a dozen, right? Because you could test a dozen within the time that you have allotted to do. Or even better, right? If you had a really powerful computer, you could do thousands, right? Or even better, you could do millions and probably approach what is the optimal design given your input. Now, the thing about this is that you notice that if we go back here, this is sort of, close to manual. This is like, the next one is, this is sort of desktop workstation power. Powerful desktop cray power, right? But to get to this level of power and this sort of thing, you need like cloud computing. You need massive computing resources. But it turns out those are sort of readily available, and I'll argue about that a little bit later. So you need a lot of compute power. So what are the challenges here beyond compute power? Well, how do you express the goals? It's sort of this user interface problem when you go to designers and you talk to them about, oh, you need to express your requirements. It can be very confusing as to what the requirements are. You automatically need to generate the designs. You need some sort of generation algorithm, right? And those of you who've tinkered around in this area, you know, yeah, there's like genetic algorithms, there's different ways of going about these things. And then you need to evaluate it in sort of a systematic manner. So that's hard. But the good news is that this approach has already worked in a couple of cases, in sort of really dramatic cases. So this was the radio antenna that NASA used from 1960 up to 2000 on most of their spacecraft. Somebody at NASA had a really nice idea where they said, hey, why don't we like design a program that randomly generates antennas, and then we'll just evaluate which one is the most effective one. And we'll run this like crazy on like a supercomputer, and then it'll pick the most efficient one. And they did it, and they found out this strange design, the design that's on the right, which looks like no human would design it unless they were into like elk or something like that. It's 90% more efficient, because that's what the computer found, right? And the thing I really liked about this, and I sort of claimed like this great intellectual insight for about a day or two, it's like, oh, it's changed the design problem into a search problem. But it somewhat did. Now the thing that's almost kind of laughable about this is you look at, in the middle of the graph there, that's the computer that did, the antenna problem, right? But your average consumer has more cycles available, more CPU horsepower available on the Amazon cloud right now, or actually as a couple of years ago, five years ago. So we really have a lot of compute power available to us. So that's sort of the good news, is that technically, yeah, it might be possible, right? The other thing I think that really drives us here is that there's something correct about this approach. Like if you think about the early days of flight, that's what this slide is supposed to show. When people tried to think about how to work on the problem of flying, lots of people built things that look like birds. So they sort of defined the problem. In order to fly, we have to be like a bird. Whereas the Wright brothers and others kind of thought, no, we need to provide a means of lift, a means of control, and a means of thrust. So they really got the problem requirements down correctly. And at that point, it became a simple matter of solving that constraint problem. But I think you get the point. There's something about this notion of, oh yeah, you're actually, when you're designing something, you're trying to get a good definition of the problem and the requirements to solve it. So in our research group, we thought, okay, let's try and build a system like this, because there's nothing like trying it to find out that's not going to work. So we said, well, we didn't say, this guy who's heading the project said, let's do a motorcycle swing arm, because he rides really fast motorcycles, and I'm surprised he's still alive. So there may be an opening in my group any day now. And it's actually a great case, because there's a vast array. Like any design space, it's pretty massive, right? There's a lot of different things you can do with a motorcycle swing arm. And this is actually sort of the way that designers work now, is they're aware of all the prior work and the requirements. They sort of knit things together to come up with a particular design. But if you break the problem down into its requirements, right? The motorcycle swing arm holds the back wheel onto the motorcycle, provides a way for suspension to allow the wheel to move up and down, has provisions so that you can have some sort of drive mechanism like a chain, has to mount to the frame or to the motor in a certain manner. So those are the actual design requirements. And we can express them in a user interface, and this is a simplified version of it, as these simple, sort of these are the forces, the stresses and strains that this particular piece has to be able to survive. And plus, roughly, we know it has to be within this volume of space, right? So there's a basic sort of shape there. Now that stuff is already sort of new, and that's the way a lot of structural engineers work nowadays. They design problems like that. The thing that I think is really important now is that if we start to include things like possible materials and possible methods of fabrication, the computer can be a lot smarter. Because there's one thing that we know from the design world is that you tend to have a design model that you make and you verify, and then you have a fabrication model, which is like, okay, given that we're building it this way, how does the model have to change? And I think by combining the two, we sort of get all the constraints, all the requirements in one shot. We'll let the computer figure it out. That sounds reasonable to me. So this is a slide of the computer figuring it out. This is just one particular design, and I think you saw it running before. And the next slide shows some variations. But it's a pretty typical topological optimization approach for those of you who are aware of that. The computer just starts out with this block of mass and starts chipping stuff away till it either fails or till it keeps on working. And it finds many designs. And you can see from here, it still leaves geometry where the spring has to be connected to the swing arm, where the chain has to go through. And it generates thousands of these swing arm designs. So we sort of have the basic plumbing of that working. What I was really interested in this is like, okay, I get it, but are people going to be able to use this thing? I mean, like, this is really weird. And so I literally took our user interface, some folks from our user interface research group, and said, can you go join those guys on this project, on the Dreamcatcher project, and just make sure this stuff is usable, find out whether designers will actually use this stuff. And so they came back and said, yeah, because the workflow does look different. There's this front-end process that we call the inspire process, where you sort of inspire the computer. These are the requirements of the problem and stuff like that. And then there's the generation phase. You generate a bunch of stuff, and you find out which ones work. But then there's this extra step in there that's not apparent, is that designers need to sort of look at all the generalized designs and find out the trade-offs between them. And we found out that a lot of designers, even if they know they cannot use that design to fabricate it, are interested in all the trade-offs involved. Like, if I make this out of aluminum, is that going to drive the cost up, or is the weight going to go up? So that they want to play around sort of like in a spreadsheet sort of way with that to navigate through that design space. So the notion of looking at the space and analyzing what's going on sort of is an important user interaction with this. And then finally, of course, you have something and you want to fabricate it, right? And so this is a video of an early version of what this thing looks like. So we're not building any geometry. There's no like 3D modeling going on. There is a 3D space where the user is exploring the various trade-offs between each design that they point to. So those green blobs there are the different swing arm designs. And I think we had like 2,000 different swing arms in the database or something like that. But you see that they're looking at, there's a different combination of strength, weight, cost, the volume of the swing arm, the time to produce, and so designers want to look at those and understand the trade-offs. I was always of the opinion like, well, isn't there just one? Like, can't you just pick one for me? But it's not, design isn't a complete science. They're trying to understand all the stuff they have to work with. So let me see if I go to the next slide here. So that was the first one. And then we did the second project where, okay, that one was pretty easy to specify the requirements for the swing arms, right? There's probably like a dozen of them. So he said, why don't we do a real case study? Okay, let's like design something from the requirements for a real car. And it turns out we found this wonderful example for Formula One racing, is you can go to the safety specs and it'll say the design requirements for like roll bar and safety cages. And so we literally pick that stuff up. And that's what this video shows. Like, we go Google, we find the requirements. This is very me. It's like, can we show Googling and finding? And there you are. Those are the requirements. So there's nothing magical here. You're an engineer. You're doing this already. And there's a diagram. And then we use a language called SysML to formalize those. And this is important because it sort of looks like this sort of strange language. But mechanical engineers already use this in sort of high-end projects. And you have the basic structural setup. You have the requirements, and you have the constraints of the problem. So it does look like a very, very different beast. And then we're into the generation phase. So this is it generating some different geometries. And actually, that was the mock-up within Maya. So it was sort of cool. Almost like a decade later, we were using Maya as sort of the back end of this thing. But anyway, so that's the example from the requirements off of a web page. It generates a legally safety roll bar cage for an F1 race car. That's the one that sort of looked like it was a sort of a normal one. Other algorithms came up with other legal ones. Everything looks all bony, And that's just because these algorithms just make geometry that's bony. We have some other guys working on another project to make it look like it's made out of an angle iron or something like that. But sort of the physical appearance of things is actually very important. I don't have a slide for it, but we did do one nice project where we said, look, actually shape is just a constraint. So we did this notion of, we have a bicycle frame in this particular shape, and it was like this super cool sweeping bicycle frame. And we asked the system to find a structure within that space that would support all the loads that a bicycle frame for the seat and the pedals and stuff like that. So we end up with this crazy lattice structure inside of it, right, that solves for all the stresses on it, but has this super cool human design shape. So I think there's there's a lot more to be done just on sort of the aesthetics and shape side. The thing that's really cool is that we had this classical bicycle problem that we were fooling around with, and these are all designed by a computer. And some of them are very similar to what humans have designed over the years, and some of them are really quite different. So it just shows that it's very pliable. It's almost like, well, let's just recompile it and try it with this constraint, and we get a new frame design. So we're building some crazy full-size bikes at the moment to see if we can actually, automatically generate a bike that's lighter than, sort of man-made one with 100 years of refinements on it. So that's the story of that Dreamcatcher project. And so, so hopefully, I've sort of argued that there's some hope. This stuff is sort of enabled by this notion that, computing becomes much more relevant when you can be highly coupled to the fabrication process. Even more coupled if you can think of matter as just being strictly a programmable thing, right? But in order to do that, especially with this approach, we need massive computing. But luckily, that's what cloud computing offers. And it nicely breaks down into this, easily computable problem. I think from a design point of view, really, it's really, at the end of the day, a great product. The design is the design of the requirements, right? That they've got sort of all the things that make you really value the product. And that's what I see as maybe sort of the hidden gem within all this work, besides just saving time. I'm not sure whether it saves time or anything, but that we'll get to a point where essentially, like with products, we'll be able to express the requirements and say, oh, it's slightly changed. Let's just recompile the product again and generate it, in aluminum or something like that. So I think that will have a lot of power. And the final point is that I've sort of found out that the computer doesn't care how complicated it is, right? It's kind of, when you think about like what happens in a lot of mechanical design, you have, the structural team has done their job, then there's a wall, and now the thermal team's working on it. And then after they're done, maybe we get the two together and make them work. But the genius of nature, this is sort of the feel-good ending to the talk. The genius of nature is nature doesn't care about complexity. There's no teams working on this thing. So it comes up through trial and error with these highly integrated, super efficient designs. And it'd be a nice trick if we could get computers to help us with some of that, right? And I think that's really what's sort of ultimately driving why I like this project and why I'm pursuing it. I don't know if we'll ever get there, but at least it's a good old college try. Yeah, so that's the end of my talk. You can find out more about this stuff on the Autodesk research site. And I'm happy to take any questions. Thank you. Ed.
Yeah, wow, you remembered. So it seems like at first glance, this approach works super well for obviously metrics that are objective, metrics that are easily operationalized, and probably not so well for qualitative metrics or kind of wicked design problems. On the other hand, we also have probably really neat tools in the kind of crowd-based space for to kind of crowdsource those questions of, is this aesthetically pleasing? Is this XYZ qualitative measure to people? Do you guys think about the crowd-based approach, or is there any place in your view for kind of
we do sort of think about it. I was telling Michael that I was sort of thinking about this stuff, and I found the soil and paper and started to look at this stuff, how we can integrate. If there's a way that integration would make sense, and what's sort of the state of the art of that stuff. There's a difference in time scale here, right? Because right now we're computing thousands of designs in microseconds. We got to wait for some crowdsource guy to do it in 30 seconds. It kind of sucks, sort of thing. So yeah, the jury's, I don't really know, but I think there's some opportunity. I'm a huge believer in the successful approach, of course, is the hybrid approach, the best of all sort of worlds. And also, fundamentally, design is a very collaborative process. And the things that we showed here are so, computer centric. It's just terrible. But at least it's a viewpoint, it's a starting point for a piece of research, right? So, sure.
Just to follow up on that question, you mentioned the word collaborative, and so that's something I'm quite interested in at the moment, is how people in different places in the world can work on the same sort of project. So are you looking into allowing sort of real-time collaboration between lots of people actually working on a model? And do you think that's the future?
That is the future, right? Maybe not thousands of people working in real time on a single model, because that's maybe not a realistic problem. But we definitely know that. Well, let me just say, like, it's almost being treated at Autodesk as not a research problem. Like, I don't see that as a research problem. It's more like, okay, what is the actual requirements that customers have to work in this way? I think we've gotten beyond sort of like, well, it's the CAD model or it's the thing. Now we're starting to look at it like someone said, well, no, it's more about the project, right? It's not the model, it's the project. And I think we'll just keep on going down that. We'll say, well, no, it's more about the cluster of people or the culture that's where, and sort of work our way up whatever chain that is. Because at the end of the day, if you look at all of our customers, they're generally almost all working in collaboration with other people. So they are already solving that problem. And I think we do a very sort of basic, basic job of supporting that. And not in any CAD specific way. We rely on them to use whatever collaborative tools are out there. But I'm not going to cite CAD. I think sort of all collaborative tools are loathsome, and it's just really, this odd thing that we haven't really nailed yet in the industry. So yeah, so keep on working on it for sure.
Cool. Really nice talk. I'm wondering if you could talk a little bit. So it seems like the Project Dreamcatcher is really trying to change the focus onto generating the design requirements, or the user needs to provide the design requirements, like, oh, it can have this much torque or this much force. So I'm wondering, have you thought about, like, how do you help people generate those design requirements, or what do you need? So for example, you show the example of, like, the Formula One racing car. Obviously they've had structural engineers and mechanical engineers figured out, like, for safety purposes, when is it going to fail? What are these things? But if you're, thinking about more end user design or something, how do you, how do you translate these engineering constraints, or how do you help people know what the right constraints should be? I'm wondering if looking forward, obviously that's not what you guys are doing.
Well, we actually started at that point. The original project was pitched to me as basically that, with this natural language interface that you could describe in pretty loose terms, the thing that you're trying to build. Like, it's a table. I want to put flowers on the table. And I'd worked on natural language, speech interfaces in the past, and I just immediately drove a dagger into the project's heart. Because I'd been burned on stage so often by speech interfaces that didn't work. However, they're working pretty well now. It's not so bad. So I think I overreacted. So we did sort of have that sense right from the beginning that sort of the natural expression of the design requirements is a thorny problem. And it is. Luckily, when we went out to customers and started talking to aerospace customers and stuff like that, they're already working in those languages to express the requirements, right? And so they do stuff like, oh, given the requirements, it's not possible for this thing cannot be, the physical laws of nature do not allow this design to work. So they're well down that road. So I think we sort of adapted the strategy. Okay, let's put that problem on hold, get the rest of the stuff working with these guys who already don't have a problem with that. They can be very technical, but eventually you do have to come back to that. And I think that's one of the maybe a really great user interface problem here. But yeah, to be determined whether we take that on. I still don't think we take it on with natural language. We also did some other stuff where we just really cool. The guys did this thing where they just crawled all the Best Buy websites and found out the basic characteristics of objects. So we could have Dreamcatcher like build us a TV stand just based on the basic requirements or the basic characteristics expressed on the Best Buy site. So there was some cute parlor trick stuff like that. And didn't fully work, but it sort of was along those lines, like how do you completely get around that problem, right? And so that stuff is pretty cool to research too. Sure.
You showed a bit of the DNA fabrication. How far along is like self-assembly going? Because it's a totally different process, right? Like nature self-assembles and builds a plant, right? We're still just putting things together and hammering them down.
Yeah, and actually, I mean, the DNA one was, I mean, the DNA does self-assemble the way DNA does self-assemble, but I mean, it's off-label usage of DNA for sure, right? It is this sort of inert object of DNA, right? There's no RNA there reproducing strands of DNA and stuff like that. How far along we on the self-assembly? We're just at the very beginning of that stuff. I think, not my area whatsoever, but I mean, people are not so much looking at this stuff so much in the assembly part as in the production of different types of molecules. Like, can we produce a molecule that takes in CO2 and generates out methane or something like that? And that's I think the sort of the state of the art at the moment. But like I said, not really my area. I'm just sort of looking at it as a CAD guy, saying, oh, there's something here that looks like CAD that I can latch onto. Yeah.
So you are using a lot of optimization procedures here. So my question is, what is the current state of the art that is being used? And the second question is, what are we looking at in the future?
Well, yeah, the state of the art for optimization, we're not doing too many super magical tricks. And I would claim that topological optimization techniques out there are probably comparable to what we're using. We have a slightly secret sauce, which we think is kind of clever and that may help us. But I think in terms of the overall approach to it, like topological optimization is only a small part. Because, I mean, think about building that part. You want to optimize not only for the topology, but also maybe for thermal properties, for all these different optimizers. So I think it's going to be how many things can you use in concert, and also things that represent the fabrication process. So the things to get right, or things we're trying to do now is let's kind of get all the components that we need to make this thing actually be useful on the table, as opposed to try and push the envelope on topological optimization and stuff like that. Although, I mean, there's folks on my team that probably they're sort of working on that, especially with regards to how it interacts with fabrication and stuff like that. But I really don't know enough details. If that's sort of your area, it's like, no, totally not my area. So.
How does the computation scale with the number of constraints? Is it exponential in the number of constraints?
That's a good question. I don't know offhand. I mean, yeah, honestly, I don't know offhand. I mean, the good thing about this approach is that you can still get results. You're not fully exploring the space. Because what we don't mention here is these spaces are huge. They're probably uncomputable, even with Amazon. Oh my God, even with Amazon, we get, but we're doing a bunch of tricks, and that's okay, right? Because we're, we didn't guarantee an optimized design. Maybe in the future we will. But at least we're sort of tricks to reduce the space and sample it and stuff like that. But to me, as an HCI guy, I'm like, okay, let's just get some stuff from plumbing in place and just take this car around the block and see what it's like, as opposed to let's make sure it's generating 500 horsepower and optimized designs. Because I don't know if people are going to want to use this stuff. I was proven wrong because when we showed this to, actually we showed it to an F1 racing team, and it was the funniest phone call we've ever had. I just got to tell this story. Yeah, I've got a minute. They got on the phone with us and they say, look, we heard about Project Dreamcatcher. We've used every piece of software out there. We don't want to hear about any commercial software. We just want to understand Dreamcatcher and how far along you guys are. And we only have a half hour, so start talking. So we're like, I guess we found a client, So I think there's people that see the promise of it. It's a question of that. Let's just figure out if we can actually use this stuff yet. I think they're sort of getting, how to, because there's some low-hanging fruit here. Obviously you want to solve different designs at the same time. You don't want to separate structural from thermal, because if you do it smartly, you get lighter things that are, they have great thermal properties, super strong, all the super material science fiction stuff. And Dreamcatcher promises some of that. At least that's the only way I, at this point, know how to get at sort of stuff like that. Yeah.
Related to that question, yeah, I'm very curious about the trajectory through these design spaces that the model takes and how that relates to or doesn't relate to what maybe a human designer might be doing. Has there been any? It sounds like, for example, the NASA antenna was a relatively like brute force, sort of like permutation based.
It's a very small problem. Yeah.
Whereas something like designing a bicycle, enormous space. With just adding several more constraints. And I suspect that there are behavioral profiles that designers have that may or may not, that these types of software tools may be able to augment or perhaps even, give us some insight into. Is that something that people are talking about or thinking about with something like this?
Well, I'll speak for myself. I may have recognized sort of what you pointed out. I was like, how do you see this space? Like, what is the computer? Because right away when I saw the demos, I said, like, what is it doing now? What's it doing now? Like where are all the thousands of jobs? And we sort of realized, just for practical reasons, like, oh, the process died, we need to restart it. We need to see the computer designing and everything that it's doing. But you bring up a good point about, we know designers want to understand the space. What representations do we have of the space? Besides that, characteristics, and here's your line through the characteristics trade-off curve. There's typical Pareto curves and stuff like that. But we are asking, okay, is there something else here? There's got to be something else, because I mean these things are very weird. It comes back and, oh, I guess this is the design. I mean, it does seem a little empty or something. So yeah, I think that's a really good topic, and I have no idea how to visualize these spaces. Actually, I mean, just for debugging reasons, I want to visualize. Did we miss any important spaces?
All right, let's thank our speaker one more time.